Hello again, this is Galen Pickett, Cal State University Long Beach. We're talking Physics 151, and now we're moving into Chapter 11, the angular momentum. The angular momentum principle is the third of the three big physical principles that are in this course. So it's translational angular momentum is what I want to talk about first. That's Chapter 11, Section 1. So I've got a particle that is sitting here perfectly happy a distance r away from my origin right here that I've marked with an x, and it has a momentum p. And assuming that there are no interactions, you know exactly what this particle is going to do. It's going to keep going off in this direction at a constant velocity. So the momentum is not sensitive to where this origin is placed. I put the origin anywhere I want. The momentum is just the quantity of motion that the system has that's sensitive to the impulse from the surroundings. But there is another quantity that involves how much of this motion can be mimicked by an object moving in a circle at some angular velocity, omega, around that origin. And the way to get that is to figure out how much of the position is perpendicular to the, how much of the displacement is perpendicular to the momentum. So there's this quantity here. If I take the part of the displacement from the origin that is perpendicular to the momentum, and then I multiply by the momentum itself, as this thing is moving, there's no interactions from the surrounding, this r perpendicular, the r will change continually. So when it's over here, there's where the new r is, but the r perpendicular part never changes, and the momentum never changes. Here's a quantity that, again, for an isolated system, this isolated system does not change. I'm going to call this the magnitude of the angular momentum. Now, depending on what this, the exact circumstances here, if you've got geometry like I've laid out here, figuring out what this r perpendicular is a matter of figuring out what's the geometry of this triangle. So you have the r, this right angle, and the momentum. You need to know this angle to figure out how much of the r is perpendicular to the p. And there's an easy way to do that. There is a construction, a vector construction, that takes two vectors in. So it's the vector cross product. So two vectors, say the position vector crossed with the momentum vector. So there's one vector that comes in, another vector that comes in, and a single vector is going to come out of this. That's the vector that we're going to call the angular momentum. The cross product, so I have to specify a vector somehow. The r and the p are both lying in the xy plane. So the angular momentum is going to be defined to be perpendicular to both of its arguments, to both the r and the p. And that gives two choices. This angular momentum can come out of the screen. So here's like a little arrow that's coming out. Or you see the tail of the arrow going away from you. This is into the screen. So we have to figure out some way to determine whether it's in or out. And the book will give you some pictures for how to use the right-hand rule. But this cross product can also be done by means of a discriminant of a 3x3 matrix. So it's a very strange discriminant of a 3x3 matrix, a determinant of a 3x3 matrix. So let me show you how this looks. Along the top row, you put unit vectors in the x, y, and z direction. So I'm putting I here because I'm going to be putting vector subscripts, and I don't want to get the notation all mixed up. So the top row goes the unit vector that is going in the x direction, then the unit vector that's going in the y direction. That's what this j thing is. And then the k is a unit vector that goes in the z direction for a right-handed coordinate system. That's the one that's coming out of the screen that you're watching right now. On the next row, you put the components for the r. So I have x, y, and z. That's the components of this vector here, x, y, z. And then the last, you put the x component of the momentum, the y component of the momentum, and the z component of the momentum. Now, for an object that is moving around in two dimensions, I think you can see, so I'll keep the I there, the j there, and the k there. I have x is non-zero, y is non-zero, but z is 0 because the object is in the xy plane. So there's an x, there's a y. Likewise, the z component of the momentum is 0 because this object is moving around in the xy plane. So I'll put a px there and a py there. Now when I take this determinant, I'm going to expand it by cofactors. So I take this unit vector and then multiply it by the determinant of this sub 2 by 2 matrix. So that's I hat times y times 0 minus 0 times py, which is 0. So there's no component for this angular momentum in the x direction. Then I do a minus sign, and then I knock this row out and this row. So I get x times 0 minus px times 0, so that's a 0 as well. And then I get k hat, that's the z direction, times x times py minus y times px. And this is how you get the coordinates, the z component of the angular momentum. So L is equal to r cross p. This is the orbital angular momentum, and it's the same thing as saying in the k direction you take the x component of the position and the y component of the momentum, and then you subtract the y component of the position and the x component of the momentum. This one points entirely in the z direction, so it is perpendicular to anything which is in the xy plane, so it's perpendicular to both the r and the p, and it has got, well, for our case here, it will be a constant. So that is the orbital angular momentum of an object that is moving around.